Hello ladies and gentlemen, welcome to my lecture series Modern Gauge Theory. My name is Genis, I'm a physicist. To follow the lectures you must have the knowledge of the basic lectures in theoretical physics, the special theory of relativity, relativistic quantum mechanics, and you must be familiar with calculus and linear algebra in mathematics. Now, this is lecture 1, elementary particles and their interaction.
The first particle that was discovered was the electron. It was discovered by J.J. Thomson and his team in 1897. They identified the electron as the particle of cathode rays. Then for some time only the ratio of charge and mass was known, the so-called specific charge. Until in 1909, Robert Millikan made his oil drop experiments. So he could measure the electric charge of an electron. He measured the elementary charge and multiples of that charge. According to the today's knowledge, we must say an electron is a stable particle, a free electron. No decay of an electron was experimentally observed until now. The data of the electron. Electron is a fermion because it has got a spin of a half. It belongs to the group of leptons, first generation, and it takes part in the electromagnetic, weak, and gravitational interaction. Electromagnetic, it has got an electric charge. Weak, all leptons and quarks make weak interaction. And of course, of its mass, it takes part in the gravitational interaction. But usually in high energy physics, we neglect the gravitational interaction because it's very, very weak compared to the other interactions here. The antiparticle is a positron. The mass is 9 times 10 exponent minus 31 kilogram or 511 kilo electron volt. That should be clear from the basic lectures in theoretical physics. We can calculate the kilograms by multiplying the electron volts by the elementary charge, 1.6 times 10 exponent minus 19 coulomb, and then by division of the square of the velocity of light. E equals mc squared is used here, we can say. The experimental mean lifetime is greater than 6.6 times 10 exponent 28 years. That is much longer than our universe exists. Our universe has got an age of 13.8 billion years. It has got a negative elementary charge and the parity is +1. Parity has something to do with a reflection in space. We will talk about that later in this lecture series. Then we have the photon. The photon, there is no discovery of that particle. In the 19th century, there were some experiments that show the wave properties of photons, of the light. And it began in 1900 as Max Planck had assumed that photons are particles to explain the radiation spectrum of a black body. And then in the 19th century, some other experiments were made which showed that photons are particles. There is especially the photoelectric effect or the Compton effect. Okay. Then the data of the photon. It is a boson because it has got a spin of 1. It's a gauge boson because it is the mediating boson of the electromagnetic interaction. The photon is its own antiparticle. A photon, okay, theoretically has no rest mass. Experimentally, the mass of a photon is smaller than 10 exponent minus 18 electron volt. Okay, because of the energy of a photon, we can calculate a mass equivalent by using the formula energy equals mc squared. So we get a mass equivalent for the energy of a photon. Yeah, free photon is stable until it makes an interaction with other particles. No electric charge. Parity is -1. Okay. Then the next particle that was discovered is the proton. It was the German physicist E. Goldstein who discovered the anode rays or canal rays. Then later it was found out that these rays are H+ ions. And yeah, Ernest Rutherford identified the particles as hydrogen ions in 1919 and then called them protons in 1920. Then the data of the proton. Proton is a fermion because of the spin 1/2. It belongs to the hadrons. Hadrons are particles which consists of quarks. And baryons, a subgroup, these are particles which consist of 3 quarks. Mesons consist of 2 quarks. It takes part in all interaction. It has got an electric charge. It consists of quarks which make weak interaction. Quarks make strong interaction, and because of its mass it takes part in gravity. The antiparticle is the antiproton. The mass of the proton is 1.7 times 10 exponent minus 27 kilogram or 938 mega electron volt. That is nearly 2000 times of the mass of the electron. That's the reason why the mass of an atom is nearly completely in the nucleus. The electron is very, very light compared to protons and neutrons. The experimental mean lifetime, is greater than 3.6 times 10 exponent 29 years. Much longer than our universe exists since the hot Big Bang. Here we must say, if there is a grand unified theory, God, and there are several different theories, different gods, but in all these theories, decay of the proton is included. Okay, but until now, no proton decay was observed. Yeah, electric charge is a positive elementary charge, parity +1, and we have a quark composition of up, up, down. Then we have the neutron. It was discovered by J. Chadwick in 1932. Yeah, it was identified as the other component in the nucleus of an atom. There were the protons, but an atom was heavier than the sum of the masses of the protons. So there must be another particle, and that was the neutron. And a free neutron is not stable. It will decay. The data of the neutron, it is of course a fermion again, spin a half, and like the proton, it belongs to the hadrons or baryons. It takes part in all interactions, and the antiparticle is the antineutron. The mass of the neutron is nearly the same like the mass of the proton. Okay, it's a little bit higher. Yeah, mean lifetime, it's about 15 minutes, we can say. Electric charge 0. It has no charge. It's neutral. Yeah, we have said it takes part in the electromagnetic interaction, and it has no electric charge. That needs an explanation. Okay, the total charge of a neutron is 0, but it consists of 3 quarks with an electric charge. And so there is a charge distribution inside the neutron. And yeah, the neutron has got a magnetic moment that can be measured. And so, yeah, strongly spoken, a neutron takes part in the electromagnetic interaction. There is a charge polarization, we can say, inside the neutron. Parity +1. The quark composition is up, down, down. Then we have the positron. Yeah, it was Dirac. He introduced the particle theoretically in 1928 because of the Dirac equation as a wave equation, a relativistic wave equation for spin a half particles. And then in August 1932, C.D. Anderson found the particle experimentally as he let pass cosmic rays through a lead plate and a cloud chamber. The data of the positron, it is a fermion because of its spin of a half. It's a lepton of the first generation, the antiparticle of the electron. It takes part in all interactions, but not in the strong one. Yeah, electron is the antiparticle. Mass is the same like electron. It is stable. Electric charge, yes, is now positive. And parity is +1. The next particle that was discovered was the muon. The muon was discovered by C.D. Anderson and Seth Neddermeyer in 1936. They found muons during investigations at the cosmic radiation. Yeah, muons have the same properties like electrons, but the mass is much higher. It's approximately 200 times the mass of an electron. So the data of the muon, yeah, it's like the electron fermion, spin a half, lepton, but of the second generation now. Interactions, yeah, all interactions, but not the strong one. The antiparticle is the anti-muon. Yeah, its mass is 106 mega electron volt. Yeah, that is more than 200 times the mass of the electron. It is not stable. It can decay, yeah, in an electron. And the mean lifetime is 2 times 10 exponent minus 6 seconds. It had a negative electrical charge. Parity is +1. Then we have the pion or pi meson. Yeah, it was predicted theoretically by Hideki Yukawa, a Japanese physicist. He predicted it in 1935 and it was experimentally proved only in 1947, 12 years later. Yeah, it was discovered by C. Powell, and he researched about the cosmic radiation, and there he found first the pi minus meson and then the pi plus meson. The neutral one was discovered later by R. Bjorklund in 1949. It is harder to discover the pi zero meson because its lifetime is much shorter than the lifetime of the charged pions. Okay, data of the negative pion first. It is a boson because of spin 0. It belongs to the hadrons because it consists of quarks, quark and antiquark. So we have meson here. It takes part in all interactions. Antiparticle of the pi minus is the pi plus and vice versa. The mass is 2.5 times 10 exponent minus 28 kilogram or 140 mega electron volt. It's not stable. The experimental mean lifetime is 2.6 times 10 exponent minus 8 seconds. Negative electrical charge, of course. Parity -1. And the quark composition is down anti-up. Then the values for the pi plus are the same. Okay, it has got the opposite electrical charge, and the quark composition is vice versa. That means anti-down and a normal up quark. And the data of the neutral pion has also boson, meson, weak strong gravitation, but it is its own antiparticle. Yeah, mass is nearly the same like the charged pions, but the mean lifetime is much shorter, 8 times 10 exponent minus 17 seconds. Okay, no electric charge. And Parity is -1. And yeah, the quark composition, that is mathematically a mixture of up anti-up and down anti-down. We will talk about that later in this lecture series. Then we come to the kaon or K meson. In 1944, there was some evidence found for a positive particle heavier than a pion. And in 1947, G.D. Rochester and C.C. Butler made research about the cosmic radiation again. And on cloud chamber photographs, they found a new neutral particle which decayed into charged pions. And on another photo, there was a decay of a charged particle which decayed in pions as well. And so we have for the data of the negative kaon first. It's a boson because it has got a spin of 0. Yeah, it's a hadron. Meson consists of 2 quarks, takes part in all interactions. The antiparticle is a K+. The mass is 8.8 times 10 exponent minus 28 kilogram. That means 494 mega electron volt. It's not stable. The mean lifetime is 1.2 times 10 exponent minus 8 seconds. It has a negative electric charge, and parity is -1, and the quark composition is strange anti-up. The values for the K+ are the same, but okay, it's the opposite electrical charge, and the quark composition is, yeah, vice versa. That means anti-strange and a normal up quark. The neutral kaon, it's of course a boson, hadron, meson, and antiparticle is the anti-neutral kaon. Yeah, the 2 particles are not identical. Yeah, the mass, okay, we can say nearly 500 mega electron volt. Yeah, here we must decide between 2 different kinds. It would lead too far now to explain that. We come to that later in the lecture series. Yeah, we have here something times 10 exponent minus 11 and here -8 seconds. Okay, parity -1. The quark composition is down anti-strange. The next particle is the electron neutrino. Yeah, there was a missing energy in the beta decay. And so Pauli postulated another neutral particle besides the neutron. That was in 1933. And it took over 20 years that this particle was discovered. It was discovered in 1956. Yeah, it was observed at one of the great nuclear reactors within the Cohen-Rains neutrino experiment. And yeah, that was the anti-electron neutrino. And the data of the electron neutrino, it is a fermion because of its spin of a half. It's a lepton for the first generation. It takes part in the weak interaction and in the gravitational interaction. Yeah, experimentally until now, no rest mass is confirmed for the neutrino, but there are experimental hints that the mass is not zero, that the electron neutrino has got a rest mass, but a very small one. We have a mass smaller than 0.8 electron volt. Okay. Yeah, the antiparticle is the anti-neutrino, the anti-electron neutrino. Yeah, free neutrino is stable. There's no decay. Electric charge 0. Parity -1. Okay, and then we have the next neutrino, the muon neutrino. It was discovered by L.M. Liderman and M. Schwartz and Jack Steinberger at the Brookhaven National Laboratory in 1962. The data of the muon neutrino are the following. It is, yeah, of course, a fermion, spin a half, and yeah, that is the neutrino of the second generation. Yeah, interactions weak, gravitation. The antiparticle is the anti-muon neutrino. Here we have, yeah, found out until experimentally that the mass must be smaller than 0.19 mega electron volt. Yeah, and this neutrino is stable as well. And yeah, no electrical charge, parity -1. Yeah, and then there was an inflation of new particles. Some new particle accelerators were built and introduced, and so much higher energies could be produced in the accelerators, and so more and more new particles were found, and yeah, many of them made a decay very fast, especially baryons and mesons. And so the assumption was made, oh, are these elementary particles all elementary, or are there more fundamental particles? And then Murray Gell-Mann developed the quark hypothesis at the beginning of the 1960s. And so this hypothesis says hadrons consist of quarks, baryons consist of 3 quarks, and mesons of 2 quarks, quark-anti-quark combination. And first, only 3 quarks were known, up, down, and strange, to explain the particles like proton, neutron, lambda baryon, and so on. And later, 3 heavier quarks were found, charm, bottom, top. Then we have the omega baryon. The quark theory predicts a new particle, a negative charged one. It is called omega, and that should consist of 3 strange quarks. And Yeah, indeed, it was produced then at the Brookhaven National Laboratory in 1963. And though that was a confirmation of the quark hypothesis. The data of the omega baryon, okay, it's a fermion, because spin 3½ Yeah, it's a hadron baryon. It consists of quarks, 3 quarks. It takes part in all interactions. The antiparticle is the anti-omega particle. The mass is nearly 3 times 10 exponent minus 27 kilogram, or 1672 mega electron volt, very heavy. Then it is not stable. It has got a mean lifetime of 8 times 10 exponent minus 11 seconds. Electric charge, yes, negative. And parity is +1. And yeah, we remarked that the quark composition is strange. Here a problem appears. A strange quark has got a spin 1/2. And so we have got here 3 identical fermions. And there is the Pauli exclusion principle. It says that no 2 or 3 identical particles can be in the same state. Here we would have 3 identical particles in the same states. So here there must be a quantum number or a property of quarks which makes a difference between the 3 strange quarks. Yeah, today we know quarks have got a color charge. And so here we have 3 different colors in the 3 strange quarks: red, blue, green. And though the Pauli exclusion principle is satisfied again. Okay. Then, we come to the discovery of the next quark. That is a J-psi meson. It has got a double name because 2 groups discovered it at the same time. It is the charm quark that was experimentally proved by producing the J-psi meson in 1974. There were some indications for another heavier quark before, and there were the groups of B. Richter at the Stanford Linear Accelerator Center and the S.C.C. Ting group at the Brookhaven National Laboratory. And so, it has got a double name then. And the J-psi meson consists of a charm and anti-charm quark. That is also called charmonium. The data of the meson, it's a boson, of course. A hadron consists of quarks, 2 quarks. It takes part in all interactions. It is its own antiparticle because the quark composition is charm, anti-charm. The mass is 5.5 times 10 exponent minus 27 kilogram, or 3 giga electron volt. It has got a mean lifetime of 7 times 10 exponent minus 21 seconds. No electric charge. Parity of -1. Okay. Then we have the tauron. After the electron and the muon, there is a third lepton that was discovered in 1975 by M.L. Pearl and at the Stanford Linear Accelerator Center. Yeah, it's of course a fermion, like the other leptons. That's now a lepton of the third generation. It takes part in all interaction, but not in the strong interaction. Antiparticle is the anti-tone, and it has got a mass of 1.77 gigaelectron volt. Mean lifetime, yeah, 3 times 10 exponent minus 13 seconds. Negative electric charge. And parity +1. And then we come to the epsilon meson. It was discovered by the group of Alan Liderman at Fermilab, Batavia, Illinois in 1977. Yeah, so it was a proof of the existence of the bottom quark, because the epsilon meson is a combination of a B quark and an anti-B quark. So the data of the epsilon meson are, okay, the boson is the meson, hadron interactions, yeah, it takes part in all interactions. Mass, very high now, 9.5 gigaelectron volt. Mean lifetime, yeah, 10 exponent minus 20 seconds. No electrical charge. Parity -1, yeah, quark composition, bottom, anti-bottom. As the next, we have the gluon. Okay, a free gluon cannot exist. It's the same like a free quark, because it has got a color charge, and yeah, we see only a white color, we can say, at particles. And it is indirectly discovered, we must say. In 1978, the Pluto detector at DESY, that means Deutsches Elektronensynchrotron, Hamburg in Germany, German electron synchrotron, they showed the first evidence. Then next year, Petra and at DESY again, and then 1980, yeah, the Jade, Tasso, Pluto at DESY, yeah. These experiments could prove the existence of gluons. If we look at the particle baryon with quarks, then the energy, yeah, there is some energy which is in the gluons, and the mass or energy is not only in the 3 quarks of the particle. The data of the gluon, it's a boson, yeah, the gauge boson. It is the mediating boson of the strong interaction. And it takes part in the strong interaction because gluon itself has got a color charge, or 2 color charges. We'll see later then. It is its own antiparticle. Yeah, we have a theoretical rest mass of 0, and the experimental value is smaller than 1.3 mega electron volt. Yeah, the mean lifetime, experimental mean lifetime, it's a stable particle. If it would be a free particle without interactions, yeah, no electric charge and parity -1. Okay. And then we have the W and Z bosons. They were experimentally found with the SPS at CERN, the Super Proton Synchrotron, at the European Nuclear Research Center in 1983. There were C. Ruppia and S. Van der Meer, which received the Nobel Prize in 1984 for the discovery of these gauge bosons of the weak interaction. So, yeah, we have a positive and a negative W boson and a neutral Z boson. Yeah, they're bosons, gauge bosons. They take part in the weak and gravitational interaction. Yeah, the antiparticle of the W plus is a W minus and vice versa, and the Z is its own antiparticle. They have a very high mass now. The W boson has got 80 giga electron volt and the Z has got 91 giga electron volt. The experimental mean lifetime of the W boson is 3 times 10 exponent minus 25 seconds. And for the Z boson we have 2.6 times 10 exponent minus 25 seconds. The W bosons have got a positive or negative elementary charge, and the Z boson is neutral, it has no charge. Parity is -1 for them. Then we come to the top quark. Yeah, it is possibly the last quark. It was experimentally discovered with a tevatron at Fermilab, Batavia, Illinois in 1995. Okay, the data of the top quark, it's a fermion because spin half, hadron. It is, okay, that's a mistake, it's no meson. Yeah, quark and anti-quark together would be a meson. Third generation. And it takes part in all interactions. And the antiparticle is the anti-top quark. And it has got a mass of 172 giga electron volt. Yeah, that is very heavy. Mean lifetime 5 times 10 exponent minus 25 seconds. Yeah, electric charge is plus 2/3 of the elementary charge, and parity is +1. And then what is missing? The tau neutrino. Yeah, as the last lepton, the second neutrino of the third generation. Yeah, this is possibly the last lepton, perhaps. It was announced in 2000 because it was discovered by the donut experiment at Fermilab, Batavia, Illinois. the data of this neutrino. It's a fermion, of course, spin a half, lepton third generation, interactions, weak in gravitation. The antiparticle is the tau antineutrino. It has got a mass of 18, smaller than 18.2 mega electron volt. Yeah, I'd recognized that. We don't know the exact rest mass of the neutrinos, but we can obviously say the neutrinos have got a rest mass, but a very small one. It is, like the other neutrinos, stable. The free neutrino is stable. No electric charge and parity -1. And then we come to the Higgs boson. The Higgs boson was produced for the first time at the LHC, the Large Hadron Collider at the European Nuclear Research Center in CERN in 2012. The data of the Higgs boson, it's a boson, and it makes weak and gravitational interaction. It is its own antiparticle. It has a mass of 125 gigaelectron volt. Its mean lifetime is 1.6 times 10 exponent minus 22 seconds. No electric charge. No spin 0, parity +1. And now we come to the last elementary particle, the graviton. At LIGO, that means the Laser Interferometer Gravitational Wave Observatory, Hanford, Washington and Livingston, Louisiana. Gravitational waves were measured for the first time in 2016. Data of the graviton, it's a boson because it has got a spin 2. It's a gauge boson, the gauge boson of the gravitation. So, in quantum field theory, we must have a mediating boson for the interaction, and here it is the graviton. It is its own antiparticle, and the mass is smaller than 6 times 10 exponent minus 32 electron volt. It could be that a graviton has got no rest mass, but often in the theory it is calculated with a positive rest mass of a graviton. Okay, we must see in the future whether a graviton has got a rest mass or not. It is stable, a free graviton, no electric charge, parity is +1. Okay. So that was an overview of the elementary particles. And now we will look at the interactions. Here we have a table with the elementary particles. We have here the 3 generations of quarks. Here up, down, charm, strange, and top and bottom. And in green here below we have the 3 generations of leptons, electron with its neutrino, muon with its neutrino, and the tauron with its neutrino. Then we have the gauge bosons, gluon for the strong interaction, a photon for the electromagnetic one, Z and W bosons for the weak interaction, and the graviton for the gravitational interaction. And we have here the Higgs boson, which follows theoretically from the electroweak interaction. It was theoretically predicted by Peter Higgs, and yeah, we had talked about that. It was found experimentally then later, and so the electroweak theory is experimentally completely confirmed. The electromagnetic interaction, is between all particles which have an electric charge. The mediating boson is a photon. Here we can say QED, that means quantum electrodynamics, is the best theory we have, because theory and experiment coincide completely here. So it is the best understood interaction, and all the classical Maxwell equations for electrodynamics follow from elementary gauge transformation. That means from first principles, very elementary. We will see that later in another lecture. Weak interaction, all leptons and quarks take part here, and the mediating bosons are the W and Z bosons. Strong interaction is between all quarks, and the mediating boson is a gluon. And gravitation, all particles with a mass, rest mass, have a gravitational field, and the mediating boson is a graviton. So here we have then other tables. Here the leptons. The leptons are arranged in 3 generations. In each generation we have a lepton together with its neutrino, and we have a total lepton number in an elementary particle process reaction, or we have the electron number, the muon number, and the tauer number. And normally we must say the total lepton number is conserved, but although only the electron, muon, and tau number is also conserved in any process with lepton particles. So here we have a table with the lepton quantum numbers. Okay. The muon and tau are not stable. Here we have typical decays. Muon decays into an electron, and together with 2 neutrinos, the muon neutrino and an anti-electron neutrino, we see the quantum numbers are conserved. We have here only a muon number of +1 on the left side. +1, that is the muon neutrino, +1, and here we have +1 and -1 in the electron quantum number. Okay. We find the same here in the decay of the tauon. It decays into also electron and anti-electron neutrino, and we have here now the muon, the tauon neutrino on the right side. Or it can also decay not into electron but into muon, but then we have an anti-muon neutrino here. Muon or tauon here we consider can also decay into hadrons. That means quarks are produced. The most possible reactions are the following. Tauon decays into, again, the tauon neutrino and negative pi meson. We see here, the electrical charge is conserved and the tau number is conserved. Or here we have a decay into 2 pions. Here we've got another neutral one if there is enough energy to produce those particles. And all the normal quantities are conserved. We have the conservation of the electrical charge, the tau number and the quark number, we can say. The quark number is 0 because we have also quark anti-quark here in the pi mesons. The quarks are also arranged in 3 generations. We have up-down, first generation, then charm strange, second generation, and top and bottom, the third generation. Of course, we have the same 3 generations for the antiparticles, for the antiquarks, of course, with opposite electric charge and so on. We have here a table with the quantum numbers, and you can look at this. The electric charge, we have -1/4 and +2 1/3 and +2/3 in the electric charge. We have isospin, baryon number, hypercharge, strange charm button, top quantum number. We consider some decays. We begin with the heaviest quark, top quark. It can decay into a bottom and a W+ boson. And out of this W boson we can get electron and anti-electron neutrino couple or quark anti-quark couple. And then the same in the other reactions here. The bottom quark can decay into a charm and W. Charm can decay in strange and W. Strange can decay in up and W, or up can decay in down and W, or vice versa, down in up and W. If we consider processes of the strong interaction, then the quarks will change the color charge. A gluon wears 2 colors, color and anticolor. For example, if we have a green quark, then we can get a blue quark plus a gluon with the color charges green and anti-blue. Or another example, we have a red quark and it becomes a green quark by emitting a gluon with the colors red and anti-green. Then we look at the strengths of the different interactions. We want to compare them. And if we want to compare the strengths of interactions, we look at the coupling constant. So the strongest interaction, that is the strong interaction, so we have a coupling constant of about 10, mediated by gluons. The electromagnetic interaction, the coupling constant is represented by the fine structure constant, that is 1 divided by 137, mediated by photons. Then the weak interaction is much weaker, 10 exponent minus 6, mediated by W and Z bosons. And the gravitation, and we see we can neglect it, the gravitational interaction in particle processes. We have 10 exponent minus 39 as a coupling constant, and the mediating boson is the graviton.
Now we finished lecture 1. Next time in lecture 2 we will talk about the action principle and the field equations. Thank you for watching. See you next time. Goodbye.